Saturday is taking you well. Thank you for attending last evening's knowledge sharing on bridge engineering, introduction to bridge engineering. There was a question raised by one of you about the stiffness of bearings and then references where they can who specify or which reference we can get the stiffness from. I think in the response we noted that bearings are manufactured by specialist firms like the Magebas, the Fresinets, the VSL, and others. And so normally engineers do design the bridge decks, get reaction values for dead load, live loads, and other applicable loads, considering also the deformation and other things. So those are information that you supply to the manufacturer of the bearing, and they tailor the manufacturer to that particular bridge. I also promised I would look for some literature and share with you. And now I got some literature. We had a training with Oriental Consultant Global 2018-19, and we were taken through long span bridge design, construction, and maintenance. And so bearing was one of the subjects matter we were taken through. And so here is a bit of a quick review, just trying to go through, and then I'll later on share with you the information. Okay. Type of bearing: we have a steel bearing, we have rubber bearing, we have selection of bearing type, and then comparison of expansion joint type and expansion joint type. I think they're competed. So this is the content. In regard to type of bearings, you see in this table we have item, that is material, resistant for horizontal force, resistant for earthquake, seismic intensity, and function. While in the bearing functions, we have steel, rubber, then these are signs giving you X is telling movable bearing, then circle is indicating fixed bearing, still remain as steel bearing in the bearing type, and then the bearing functions. So these are some of the symbols they normally indicate. And then distribution, they're saying that seismic horizontal force distribution bearing. So these are under the bearing type, and then the bearing function. And then damping, you have base isolation bearings. Then level 1, level 2 for seismic intensity. These are levels of earthquake. You have base isolation bearing and type A bearing. So most of these bearings are given. Level 2, I think, has type B bearing. And then I think down, integrated and separated, function integrated bearing and function. So basically these are some of the bearing types that look at. So if you look at the steel bearing, you can see how this is demonstrating the transverse detail. This is the superstructure. That's it could be girder. This is a girder here. You have a sole plate. You have upper SU. You have the SU base motor, and then you have the anchor. These bearings also do. You must have the anchor, the plates. The plates which encapsulate the bearing are held by holding down balls to be firm. When these bearings are performing, the plates will remain firm. So the longitudinal section you can see here, giving you the detail. Then for rubber bearing, it is very clear. It is highlighted here, arch. So you have your superstructure girder here, and then you have this sole plate. These are details. You can still research more and get to understand some of these. So these are the details. So if it is a rubber stuff, this is how it looks like. Then it's telling you, I can see this area, this is locking this not to move. The whole body here is keeping this bridge, the bearing, the girder here, kept in one position. They call it fixed. While here, it can move. You can see there's no locking device on the sides. So in the transverse, it cannot move, but in the longitudinal, it moves. That means in event of temperature, earthquake, breaking, another thing, the bearing allow movement. But the bearings don't allow movement up to about, I think, 25 or 20, depending on. So that one you can read. Then steel bearing, these are line bearings. Some of these, of course, I've not seen myself. I can't claim that I know everything. No. I think we are more into pot bearing for this bridge of the flyover, the Simba, the Component Expressway, the Para, yeah, and then smaller river bridges we have elastomeric bearing. I think Logogo also had elastomeric bearing things. So you can see how this bearing perform here: rotation, sliding, upper sue, blah blah. Applicable for small bridges less than 30-meter length. It is even here. So if you have your steel plate, this is how the whole thing is locking down here. And this is a typical one. This is now together with the girder. Not applicable for skew bridges due to one directional rotation. I think there's someone who is doing an assessment of the behavior, the impact of access road to Karuma. Karuma looked to be skew, though the bridge remained rectangle, but the road skews to Oro. The road is skewed to the bridge in a way. So when you are coming, normally vehicle get problem as they are turning. They don't make full turn. They make half turn, then the complete turn is on the bridge, which is has claimed a lot of lives and fatalities. So not recommended to use as movable bearing due to easy abrasion at contact surfaces. These are basically steel stuff. These are the different parts. Now this is the mechanical. Well, as an engineer, really, it is good to know, because if some of these elements have lifespan. So if their lifespan are not tailored or not matching the bridge, that means you need to know. If it is 15 years, 20 years, definitely now you know either they can replace this other element or the entire unit can be replaced. So most bridge bearings do have about 15 to 20 year free maintenance life, beyond which becomes a bit risky to accommodate loads that it is ever increasing while the condition is deteriorating. Bearing plate will be damaged. Now you can see the bearing plate. So these are things that get damaged, and that's why it necessitates timely inspection. So if there's any problem because of exceptional loads beyond limits, then you are able to arrest the situation early enough. The BP-B type is more durable based on stability of fluorine treatment plate in site experience. Okay, there are two types. You have the BPA and the BP. So you can actually look at it and get to understand. These are pin bearing types are here. We have seen this one, I think, if I'm not lying, Karuma and Karumba, Sezibwa, Okolo, and Pakwach. They are not very far from this. One direction rotation, able to design with large vertical loads. So it's more you design, you get your reaction. Once you have that reaction, definitely all this can be. So these are kind of details, and we're done. Pivot bearings, definitely I know rotation in all direction. So cuff bridges and other things are So able to design with large vertical loads also. Then we have roller types. You always hear lecturers giving you pin roller. So this is how the whole thing is: single roller, pin roller, multi-roller, pivot roller. Roller responsible for slide and rotation, not applicable for skew bridges. So you need to understand how do skew bridges work. It's very important with all this. You see they're saying this is not applicable, this is not applicable. So you need to take note of that. Now then pin roller also is on a one directional rotation. For all directional rotation, that's the pivot type. Then your rubber is here. Mainly applicable to short span concrete bridges. Very good. They are here. This one, that one, this one, and that one. Very simple. Unapplicable. Then this is a movable or fixed type bearing. This is now where they tell you, they are giving you the different, the elastomer. Let's say I talked about the rubber type, then the steel seams. These lines here are the steel plates are here, then you have the rubber, so it's more of reinforced kind of. It's a bit strong, can take a bit of. So you can see they're used in earthquake area, level A, level 1, type A, and type B for level 2 earthquake. Okay, so so this is basically about bearings. You can see these are not civil engineering things, these are mechanical kind of, but they help us a lot as civil engineers. So once you have your loading, you supply and you should be able to get it. These are some of the, so these are steel plate housing the bearings in. These are you see the black thing here, down here, and then you can see the way they are fabricated. So this one resists horizontal slip by shear deformation of rubber. So when you're designing rubber, you must also, it will also give you the shear deformation. You read about this. Resist horizontal slip by side block. This side block here, you see even they've circled for you, so it cannot slip. This is the rubber bearing continuous. So rubber bearing, movable and fixed type, but they are encased more or less. They have plates still robust on the side and it is inside, and there is some allowance, doesn't exactly touch, so try to note that. They are here, and it is here. This is your steel plate girders or roll girders, and these are the side blocks. So it allows, you may find these are balls, so in a way it can move from up but down, has a bit of a bit locked. So the whole thing here from this move like that, and a load like that. Down, you can see those the protruding stuff here. It appears to be subsisting. It is even here all around. So okay, distribute horizontal seismic force to substructure by shear stiffness of rubber. This is now what we are. What is that shear stiffness? Is what the question Gonza asked yesterday. How do we use that? And in our models, when you are doing models of bridges, and this actually here is the substructure or the abutment self or pier support system. Then in between here and this, the bottom of the plate is the elastic what? This elastic link. This elastic link now is the one that you define the stiffness, now the properties of this bearing here. So that's what normally do, and this is it. When you're modeling, you can see a rigid link up from the top of the slab coming to the bottom. Then there is a connection here with the elastic link. This is now the one, and the stiffnesses you can calculate when you design and you calculate that. You can now compare the calculated stiffness. Then you compare with what it is here. If they match you, then you order the bridge. If the plan dimensions are okay and the stiffness is fine, then you should be able to do that. This is now how the rubber bearing, the base isolation, you can see. This is how your steel plates are here. High damping rubber and you know very well that this high damping stuff they're used in earthquake prone areas which have a bit of substantive kind of lateral movement, earthquake zones and other things. So these are selection of bearings type. This is from a consultant perspective. You as an academia, you can now pick some of these and read wider in this. So we have steel bearing. The bearing types are here. You have bearing plate, pin bearing, pivot bearing, roller bearing, movable fixed. Then you have up. There is a steel here which is 1, 2, 3. Then up rubber is movable, stroke fixed. Then seismic horizontal force and base isolation. Then on a bearing type, that's it. Then the loads are here. Vertical loads are here. You see the range from 300 kilonewton to 25. This is about 3,000 onward. 3,000. These are the range. So as soon as you calculate your reaction and other things, you can easily pick from here. Then the span type also given. 20 above, 50, 50, 20, blah blah. Then support conditions are all given here, movable, fixed, blah, blah. Simple girder, then this. So now this is where you need to know what is this double ring. Single ring, I think it is a fixed. Or double is movable stroke fixed. Simple girder, movable. So these are like, we saw it up there. We saw it, I think, here. Say this, if it is movable, it is X type. If it is fixed, it's like a ring. So we need even this. I think should be defined somewhere down here. We need to see the triangular, double ring, triangular, then one circle. So advantage, we shall try to see. We shall find where it is defined. It's very important, because these are symbols that we use, but this circle one is always fixed. Then free is like, it's not shown actually here, it's like a cross. Then there is one when you allow on a movement in one direction, then you see it's not a cross but the arrows, both sides facing that and the other side fixed. But here it's slightly different the way the consultant did this. Of course, you as student, we shall get the explanation for this and try. So the advantages are here: economical for large stress slide, blah blah. All of this one. This one, this actually here. If you look at Anna Steel, it's telling us that in most cases these are fixed. In most cases. For simple girder, they are fixed. For continuous girder, they also fix. Actually, they fix for all. All this one is fixed, that one is fixed, that one. But for simple girder, this is another type. I don't know which one, but it is for this range of span. But for this range of span, they are fixed. Now I understand it now. And then for continuous girder, they fix it all. Then for arch type, I think this dash, I don't understand, but for the pin bearings, bearing plate, they leave it. I think not applicable. This is not applicable here, and it is on the pin bearing or pivot bearing. They fix them. So actually, pin bearing and pivot bearing for all this, for simple girder, continuous, and arch, they are all fixed. While this one is what I've not got it. I think I don't know what this is, but it is fixed for continuous. And this one, plate for bearing plate. Then roller type fix, and it's not applicable. And for the rubber, you have the fix, and then this triangular one also. I don't understand the symbol. It's not defined here. We shall have to wanna get it. This is a classroom, we shall check that. So for rubber, it can absorb impact, simple structure, used for simple, can distribute or dump horizontal force. Then it is uneconomical for large slip and rotation. And then for this one of steel bearing, The advantages are that they are economical for large stress, slide, and rotation, economical due to simple structure, movable, fixed type, and corrosion protection necessary. That could be there. Okay, comparison of expansion joints. So up was basically bearings. So now we have moved to expansion. This was not about expansion. Yesterday we didn't talk about expansion. May not be wise to dive into that. So what I will do is I will open for us the bearings. Yesterday we talked about bearings, and then I got some literature on where it's saying that elastomeric bearings support the bridge superstructure while allowing for vertical load transfer, horizontal movement, that is thermal, creep, and shrinkage. Of course, there are other movements. I think sometimes these philosophers also keep quite wrong. Even when you're on the bridge, the braking time, friction, braking, the bridge moves in both vertical, horizontal, you get it, even sideways. So that is something that you need to do that. Horizontal movement, that is that. Rotation as support, then vibration isolation. Their behavior is governed by the stiffness of the laminated rubber stack. I told you have steel, you have the rubber, you have steel, rubber, forming like a reinforced kind of member, or composite member. Key stiffness components are, we have shear stiffness, Ks, which controls horizontal movement, and this is the formula. That is why I was a bit, it's important that we understand this. So you guys will look at this and then do a bit of research, and so whereby Ks is the stiffness, A is the plan area of the bearing, G is the shear modulus of rubber. Typical values are 0.8 to 1.9, but for bridges normally it's recommended to use 0.9, but you can still cross check, there's no worry. That is something you do. And then TR is actually the total rubber thickness, sum of internal layers. So that would mean if you have designed you have the load, you have determined the thickness of your bridge, the bridge bearings, and then you know you have the different layers, steel, rubber, give you the total. Then you now get, you must now, because they are telling us TR is the total rubber thickness, so it means sum of internal layers, rubber. I think basically I don't think we include the steel there, but of course we have to check. So rubber is soft in shear, so it allows the bridge to move without large forces. Of course, you first have to, from your reaction, you first determine the bearing thickness, and then it will give you the elastomers and the steel seams or the steel plates which are part of reinforcement. Then from there, now if you want to calculate the stiffness, other things, now you can use this formula, and then you do that, because you can assume the area, everything here, and then calculate the Ks, then compare. But it's better if you, of course, the load from your bridge will give you the corresponding bearings, which bearing has that detail that you need. So you should be able to do that here. Vertical or compressive stiffness, so that was horizontal Ks, this is now Kv, controls vertical deflection, which is the area times the effective modulus. The effective modulus is given by 6 times G, and G is already defined up here, that G is the shear modulus. Then S is the shape factor here, down here, loaded area divided by free bulging area. And what is the bulging area is the perimeter times the thickness of one rubber layer. So vertical. So it's a very interesting formula. You guys, you are mathematicians, should be able to feel all this accounts for the confinement provided by steel laminates. Then rotational stiff. So actually you have three stiffnesses that we're looking at. You have the horizontal, the vertical, and the rotational. It is here. Uncontrolled rotation capacity, kV h squared over 12, where total bearing, h is the total bearing thickness. The steel, I was telling you, so the rubber is what the meaning of remove steel. Now here it is both steel and rubber. Definition of key terms, shape factor is given here. Loaded area or free bulging, and what's free bulging also is given. Meaning, IS rubber is well confined, high vertical stiffness. Low S rubber bulges easily, low vertical stiffness. Typical bridge bearing, S is between between 6 to 12 shape factor. Effective modulus EF is given by this formula, meaning although rubber is soft, steel laminates prevent lateral bulging, making the bearing behave as if it has a much higher compression modulus. Typical values are given for effective that one you can also research more and check whether all literatures, all texts, or all manuals have similar. Why these concepts matter? Student-friendly explanation is here for you guys. Shear stiffness tells us how easily the bridge can slide during temperature changes, and shear and vertical stiffness tells us how much the bearing compresses under load, and then rotational stiffness tells us how the bearing accommodates rotations from bending of the bridge deck. Remember, even maybe you have curved bridges, you have skew bridges, eccentric loadings on a bridge where a bridge is square. Eccentric loading can also generate a bit of abnormal responses, non-linear responses. So shape factor tells us how squeezed the rubber is. You see bulging effect, they are telling you to control the shape factor between 6 and 12, beyond which you are in trouble. An effective modulus tells us how stiff the rubber becomes when confined by steel. These concepts help engineers design bearings that are safe, durable, and flexible. Good. So this is how the formula is given here. The values are up here. I think this was repeated. Recommended literature. I also move further to get literature you can read, because that question was raised, and I said I'll try something and share. So this is something briefly I can share. So you have these international standards, you can look at these, and then textbooks are also here, and then practical manuals. You can look at ICE manual of bridge engineering, I think FHWA bridge bearing manual, Ashito Elastomeric. Then student ready summary paragraph. This is what we have. Elastomeric bearings are made of layers of rubber and steel that allow a bridge to move and rotate safely. Their behavior depends on shear stiffness, vertical stiffness, and rotational. And you say shear is more lateral. And then compression effect deals with the vertical, and then the rotation. Depending on the orientation of the bridge and the response, these are the stiffness that need to be known. These are controlled by the shear modulus, the total rubber thickness, the shape factor, which shows how much the rubber is confined, and the effective modulus, which represents of the already been defined out. So, ladies and gentlemen, this is a quick research I did, and I will leave the rest for you to read. And I would have shared with you guys some photographs of some of the bearings we already seen on site, but we shall do it another day. Thank you so much.